Welcome to this coding walkthrough. Today, we'll tackle LeetCode problem number 965, Univalued binary tree. In this problem, we'll determine whether all nodes in a binary tree share the same value. It's a great opportunity to practice tree traversal techniques and reinforce our understanding of binary tree properties. Let's dive in. A binary tree is considered univalued if every single node in the tree shares the exact same value. The goal of this problem is to determine whether a given binary tree meets this condition. You are provided the root of a binary tree, and your task is to return true if the tree is univalued, or false otherwise. Let's take a closer look at the input and output formats. The input is a tree node object representing the root of the binary tree. Each node has three properties: val, which is an integer representing the node's value, left, which is a pointer to the left child, and right, which is a pointer to the right child. If the binary tree is empty, the root will be none. For the output, you simply return a Boolean value, true if all nodes in the tree have the same value, or false if at least one node has a different value. Now let's go through some examples to clarify. In the first example, we're given a binary tree where the root node has a value of 1, and all of its child nodes, including the left and right subtrees, also have the value 1. Since every node in the tree shares the same value, the output in this case is true. This tree satisfies the univalued property because there are no nodes with differing values. In the second example, the root node and most of the child nodes have the value 2, but one node in the right subtree has a value of 5. Because this single node breaks the condition of all nodes having the same value, the tree is not univalued, and the output is false. Let's look at one more example to further solidify this concept. In this case, the binary tree consists of a single node with the value 3. A tree with only one node is always univalued because there are no other nodes to compare against. Thus, the output here is true. Additionally, this example highlights an important edge case: single node trees automatically satisfy the univalued property, as there's no possibility of differing values. Finally, let's consider the constraints and edge cases for this problem. The binary tree will always have between 1 and 100 nodes, so it's guaranteed to be non-empty. Each node's value is an integer between 0 and 100. Some important edge cases to keep in mind include single node trees, which are always univalued, and trees where all nodes share the same value, which are also univalued. On the other hand, if even one node in the tree has a value that differs from the others, the tree is not univalued. These constraints ensure that we're working within manageable input sizes while focusing on the core logic of determining whether the tree meets the univalued condition. To determine if a binary tree is univalued, meaning all nodes share the same value, we can explore several traversal-based approaches. The first is a recursive depth-first search, or DFS. Here, we traverse the tree recursively, checking each node's value against the root. If a mismatch is found, we immediately return false, otherwise, we continue until all nodes are evaluated. The intuition is straightforward: since a univalued tree requires uniformity, we validate each node by comparing it to the root. This approach has a time complexity of O(n), as we visit each node once, and a space complexity of O(h), where h is the height of the tree. For balanced trees, this is log n, but for skewed trees, it could be as high as n. Another approach is iterative DFS using a stack. This is similar to the recursive method but avoids function call overhead by explicitly managing the traversal stack. We push the root node onto the stack and iteratively process each node, comparing its value to the roots. If a mismatch is detected, we return false, otherwise, we continue until the stack is empty. The time complexity remains O(n), and the space complexity is still O(h), though this method is often preferred in environments with limited recursion support. We can also consider a breadth-first search, or BFS, which uses a queue for a level-order traversal. In this approach, nodes are processed level by level, and each node's value is checked against the roots. If a mismatch is identified, we return false. If the entire queue is processed without issues, we return true. BFS is particularly helpful for visualizing or debugging the tree structure due to its level-order nature. The time complexity remains O(n), as each node is visited once, but the space complexity is O(w), where w is the maximum width of the tree, or the number of nodes at the widest level. For a balanced tree, this width is typically n/2. Among these options, recursive DFS stands out as the most suitable solution for this problem. It is simple, aligning naturally with the hierarchical structure of a binary tree. The implementation is clean and intuitive, making it easy to understand and maintain. While iterative DFS and BFS are valid alternatives, they introduce additional data structures like stacks or queues, which add complexity without offering significant performance improvements for this specific problem. Recursive DFS does come with some trade-offs, such as the risk of stack overflow in cases of extremely deep trees, such as those with a height greater than 10 to the power of 4. However, these scenarios are rare in practice, and iterative methods can serve as fallbacks if needed. The key insight for this problem is that it boils down to validating that all nodes share the same value. By leveraging the tree structure, we can efficiently perform this check by comparing each node's value to the roots. Recursive traversal fits naturally with binary trees, allowing for a concise and elegant implementation. This gives us a robust solution that is efficient for the majority of cases. The final implementation encapsulates this approach neatly. The function utilizes a helper method, DFS, to recursively traverse the tree. For each node, we check if it is null, in which case it is valid, or if its value matches the roots. Any mismatch results in an immediate return of false. Otherwise, the function continues to recurse through both the left and right subtrees. This solution is efficient and concise, ensuring that all nodes are validated while maintaining optimal time and space complexity. By aligning the implementation with the tree structure, we achieve a clean and practical solution. Recursive DFS balances simplicity and effectiveness, making it the ideal choice for solving the univalued binary tree problem. The problem we're solving is called Univalued binary tree. The goal is to determine whether all nodes in a given binary tree have the exact same value. A binary tree consists of nodes where each node holds a value and has up to 2 children, left and right. To check if the tree is univalued, we need to ensure that every node's value matches the value of the root node. To achieve this, we'll use a recursive depth-first search, or DFS, approach. This algorithm is well suited for tree traversal because it systematically explores each branch of the tree. First, let's clarify the input and output. The input is a binary tree where each node has an integer value. The output is a Boolean value, true if the tree is univalued, and false if even one node has a different value. The recursive DFS process begins with a base case. If the current node is none, meaning we've reached the end of a branch, we return true since an empty subtree doesn't violate the univalued property. Next, we perform a recursive check for the node's children, comparing their values to the current node's value. If the values differ, we immediately return false and exit the recursion. This forms the foundation of our algorithm. Now, to complete the recursive DFS process, we need to examine the subtrees. Once we've compared the current node with its direct children, we move deeper into the tree by recursively checking the left and right subtrees. For each subtree, we verify that all nodes within it satisfy the univalued condition. If both the left and right subtrees are univalued, and the current node's value matches its children, we return true. Otherwise, we return false. This ensures that the result propagates back up the tree, allowing us to determine whether the entire tree is univalued starting from the root. Let's highlight a few important aspects of this approach. First, the algorithm is designed to traverse the entire tree efficiently, visiting each node exactly once. This gives us a time complexity of O(n), where n is the number of nodes in the tree. Second, the base case is critical. It prevents unnecessary checks beyond the tree's boundaries and handles edge scenarios gracefully. Lastly, the use of short-circuiting means that as soon as we encounter a mismatch, the algorithm terminates early, saving computational effort. This makes the solution both efficient and elegant. The recursive DFS algorithm relies on the tree structure itself for traversal, meaning no additional data structures are required. The recursion stack handles the process of visiting nodes, which keeps the implementation simple. To illustrate the algorithm in action, let's walk through an example. Consider a binary tree where the root has a value of 1, and all its descendants also have the value 1. Starting at the root, we compare its value to its left and right children. Both match, so we proceed to check the left subtree. Here, the left child also matches its own children, and as we move further down to the leaf nodes, we see that they are none, which satisfies the base case and returns true. Next, we check the right subtree, where the child has no further descendants. Since there are no mismatches, the algorithm confirms that the tree is univalued and returns true. This step-by-step process demonstrates how the recursive checks work together to verify the condition at every level of the tree. In solving this problem, there are a few edge cases to consider. First, if the tree is empty, meaning the root is none, the result is true because there are no nodes to violate the univalued condition. Second, a tree with only one node is always univalued since there's only one value present. The third edge case is a large tree that contains just one mismatch. Here, the algorithm is designed to detect the mismatch early and return false immediately, avoiding unnecessary traversal of the rest of the tree. To optimize performance, this early exit mechanism is crucial. Another possible optimization is tail recursion, which can reduce stack usage in languages that support it, although Python does not perform tail call optimization. Finally, let's review the complexity analysis. The time complexity is O(n), as each node is visited exactly once. The space complexity depends on the height of the tree, which dictates the maximum depth of the recursion stack. For a balanced tree, this is O log n, while for a skewed tree, it could be as high as O(n). These factors ensure that the algorithm runs efficiently regardless of the tree's structure. By carefully handling the base case and incorporating short-circuiting, this recursive DFS approach achieves both robustness and performance. It is a natural fit for the problem, leveraging the hierarchical structure of binary trees to systematically validate the univalued condition. The algorithm's simplicity, combined with its efficiency, makes it an excellent solution for this challenge. By focusing on the key operations, recursive traversal, early exits on mismatches, and leveraging the recursion stack, we ensure that the solution is both elegant and practical for binary trees of any size or shape. This implementation solves the LeetCode problem univalued binary tree using a recursive depth-first search (DFS) approach. The goal is to determine if all nodes in the binary tree have the same value as the root node. The treenode class is provided for representing a binary tree node, with attributes val, left, and right for the node's value and left/right children, respectively. The solution class contains the method isUnivalTree, which is the main function solving the problem. The isUnivalTree method takes the root of the binary tree as input. A helper function DFS is defined within it to perform the recursive DFS traversal. The DFS function works as follows. 1. It first checks if the current node is none, i.e., a leaf node has been reached. If so, it returns true because an empty subtree is trivially univalued. 2. It then compares the current node's value with the root node's value. If they differ, the function immediately returns false because the tree cannot be univalued. 3. If the current node matches the root's value, the function recursively checks the left and right subtrees by calling DFS on node.left and node.right. The result is true only if both subtrees are also univalued. Finally, the DFS function is invoked on the root node to start the traversal. The method returns the result of the DFS, which is true if the tree is univalued and false otherwise. This approach ensures that every node in the tree is visited, making it both simple and efficient. The time complexity of the solution is O(n), where n is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we begin by defining the structure of a binary tree node using a Java class called treenode. Each node has an integer value, as well as references to its left and right child nodes. The class includes 3 constructors, one with no parameters, another that initializes the node with a specific value, and a third that initializes the node with a value and its left and right child nodes. Below that, we have the solution class, where the main logic for checking if a binary tree is univalued is implemented. The isUnivalTree method takes the root node as input and uses a helper method called DFS, short for depth-first search. This helper method will recursively traverse the tree and check if all nodes share the same value. At the start of the DFS method, we pass the root node and its value as the reference value for comparison. In the DFS method, the first condition checks if the current node is null. If it is, we return true, because an empty subtree is considered univalued. Next, we check if the value of the current node is different from the reference value. If there's a mismatch, we return false, indicating that the tree is not univalued. Finally, we recursively call the DFS method on both the left and right child nodes of the current node, ensuring that all nodes in the tree are checked. The results of these recursive calls are combined using a logical AND operator, so the method only returns true if both subtrees are univalued and match the reference value. This completes the depth-first traversal and ensures the tree is evaluated for the univalued property. To understand how the solution works, let's look at a simple univalued tree. In this example, the tree has 3 nodes, all with the value 1. The DFS function begins at the root, where the value is 1. From there, it moves to the left subtree. The left child also has the value 1, which matches the root's value. The DFS function then checks the left and right children of this node, but since both are none, it returns true for these recursive calls. Since both the left and right subtrees of the left child return true, we return true for the left subtree. Next, the function processes the right subtree. The right child has a value of 1, which again matches the root's value. Similarly, both its children are none, so true is returned for these recursive calls. Since both the left and right subtrees of the right child also return true, we conclude that the right subtree is valid. Finally, because both the left and right subtrees of the root return true, the entire tree is univalued, and the function outputs true. Now, let's examine a tree that is not univalued. In this example, the root has a value of 2, and its left child also has the value 2, while the right child has the value 5. The DFS function starts at the root and proceeds to the left subtree. The left child's value matches the root's, so the function continues to check its children, which are both none. These return true, so the left subtree is deemed valid, and we return true for it. However, when the function moves to the right subtree, it finds that the right child has a value of 5, which does not match the root's value of 2. This mismatch causes the DFS function to immediately return false for the right subtree. Since the right subtree is not valid, the entire tree is not univalued, and the function outputs false. Finally, let's consider a tree with just a single node. In this case, the root is the only node, and its value is 7. The DFS function starts at the root and checks its left and right children. Since both children are none, the function returns true for these recursive calls. With both the left and right subtrees returning true, the root itself is considered valid. Since there are no other nodes to check, the entire tree is univalued by definition, and the function outputs true. The time complexity of this solution is O(n), where n represents the total number of nodes in the binary tree. This is because the algorithm employs a depth-first search, or DFS, starting at the root node and visiting each node exactly once. For every node, we perform simple operations such as checking if the node is null and comparing its value to the root value. Each of these operations takes constant time, or O(1). When you sum this up across all n nodes, the total time required becomes O(n). This makes the algorithm highly efficient in terms of the time it takes to traverse the entire binary tree. Now, let's discuss the space complexity, which is O(h), where h is the height of the binary tree. This is a result of the recursive nature of the DFS traversal. At any given point, the recursion stack holds function calls corresponding to the nodes along the current path from the root to a leaf. In the best-case scenario, where the tree is perfectly balanced, the height of the tree is log n, leading to a space complexity of O log n. In the worst-case scenario, such as in a completely unbalanced tree that resembles a linked list, the height becomes n, resulting in a space complexity of O(n). It's important to note that no extra data structures are used, so the space complexity is entirely determined by the depth of the recursion stack. When comparing this optimized approach to a brute force method, we can see clear advantages. A naive approach might involve traversing the tree multiple times, for instance, by collecting all node values in an array and then checking whether all values are the same. This would increase the time complexity to O(n) for traversal plus O(n) for the comparison, resulting in O(2n), which simplifies to O(n). Additionally, the array would require O(n) extra space. In contrast, the current DFS approach performs all checks during a single traversal and avoids extra memory allocations, making it both time optimal and space efficient. For specific cases, the best case scenario occurs when the tree is perfectly balanced and all nodes share the same value, yielding a time complexity of O, n, and a space complexity of O, log, n. In the average case, the tree may be partially balanced with mixed values, where time complexity remains O, n, and space complexity is determined by the height of the tree. The worst case arises when the tree is completely unbalanced, where both time and space complexity become O, n. Finally, let's break this down mathematically. Each node contributes a constant amount of work, O1, during the DFS traversal. Since all nodes are visited exactly once, the total work amounts to O1 multiplied by n, which equals O(n). For the recursion stack, its depth is dictated by the height of the tree. In the worst-case scenario, where the height of the tree equals n, the space complexity becomes O(n). Meanwhile, in the best-case scenario, where the tree is balanced and the height is log n, the space complexity is O log n. These calculations highlight how both time and space complexity are tightly connected to the structure of the binary tree and reinforce the efficiency of the DFS approach. When tackling this problem, there are a few common pitfalls to watch out for. First, assuming that the tree is always non-empty can lead to errors. If the input tree is null, it's important to explicitly handle this edge case by returning true, as an empty tree is considered univalued. To fix this, you can add a base case that checks if the root is null at the very start of your function. Another mistake is comparing only parent-child nodes directly. Remember, a univalued binary tree requires that all nodes, not just adjacent ones, share the same value. This often arises from incomplete traversal logic. To avoid this, ensure your traversal visits every single node and compares its value to a consistent reference, like the root's value. Additionally, iterative solutions can sometimes go wrong if stack or queue management isn't handled properly. Missing nodes or introducing infinite loops often happens due to forgetting to push both left and right children into the stack or queue when they are non-null. Lastly, hard-coding specific values for comparison, like checking if a node's value equals 5, can lead to issues when handling dynamic inputs. Instead, use the root node's value as the reference for all comparisons throughout the tree. These small adjustments can significantly improve the reliability of your solution. Now, looking at performance and interview preparation, it's crucial to think about time complexity. Inefficient solutions, like revisiting nodes multiple times unnecessarily, can lead to poor performance, especially for large trees. To optimize, aim to visit each node only once using either a depth-first or breadth-first traversal. During interviews, it's also important to discuss edge cases. Be ready to explain how your solution handles scenarios like an empty tree, a single-node tree, or a tree with varying depths where all nodes still have the same value. Another key point is traversal flexibility. You might be asked to implement the solution using both recursive and iterative methods, so practice both approaches to ensure you're comfortable switching between them. Additionally, be prepared to discuss space complexity. For example, recursive DFS uses O, H, space, where H is the height of the tree, while iterative BFS requires O, W, space, where W is the maximum width of the tree. Highlighting these trade-offs can impress your interviewer. Lastly, show your understanding of tree traversal patterns like preorder, inorder, postorder, and level order, and explain how they relate to solving this problem. This demonstrates a strong grasp of tree algorithms in general. This problem also connects to several related problems that you might encounter. For example, LeetCode 100, same tree, involves checking if two binary trees are identical in structure and values. LeetCode 101, symmetric tree, asks if a binary tree is symmetric around its center. LeetCode 104, maximum depth of binary tree, requires finding the maximum depth of a tree, and LeetCode 572, subtree of another tree, challenges you to determine if one tree is a subtree of another. These problems share traversal techniques and can deepen your understanding of binary tree operations. In terms of alternative approaches, recursive DFS is a straightforward method where you traverse the tree recursively, ensuring that all nodes match the root value. However, this approach can lead to stack overflow for very deep trees due to its O, H, space complexity. Iterative BFS, on the other hand, uses a queue for level order traversal while comparing each node's value to the root. This avoids recursion and handles deep trees better but can be slightly more complex to implement. Iterative DFS, which uses a stack, is another option. It mimics the recursive process but avoids function call overhead. This approach also requires careful stack management to ensure all nodes are processed correctly. Understanding when to use each method is key to solving variations of this problem efficiently. To wrap up, the most efficient solution to this problem often depends on the constraints, particularly the depth of the tree. Recursive DFS is typically the cleanest and easiest to implement, making it a great first choice. However, if you're dealing with very deep trees and stack size becomes a concern, switching to an iterative approach, either using a stack or a queue, can be more reliable. By balancing simplicity, performance, and space usage, you can adapt your approach to suit the specific requirements of both the problem and the interview setting. Great work! To recap, we solved the Univalued binary tree problem by implementing efficient traversal algorithms. We also discussed the time and space complexities, along with key takeaways like handling edge cases and using recursion effectively. Thanks for watching, and see you in the next coding session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!